In this lab, we're exploring the motion of an Atwood's machine, which is a simple device used to study Newton's second law and the relationship between force, mass, and acceleration. The setup includes two different masses connected by a string that passes over a pulley. Because of the difference in mass, the system accelerates, allowing us to measure both the theoretical and experimental accelerations. In this first part of the lab, we'll use a single pulley to observe how the system behaves and calculate the acceleration based on our data. Then, in the second part, we'll add another pulley to see how a more complex setup changes the acceleration and the overall motion. By comparing our experimental values to the theoretical ones, we can evaluate possible sources of error, such as friction in the pulley or unbalanced mass. Overall, the goal of this experiment is to better understand how Atwood's machine demonstrates the law of motion and how real-world factors can influence ideal physics predictors.
So for the materials, we pretty much just used our iPhones for the camera to record everything, the capstone program, and then the motion sensor.
Hello everyone, for this experiment we used the Atwood's machine to study the relationship between the mass and the acceleration. So we began by selecting two different masses. We labeled them M1 and M2, making sure that M1 was heavier than M2. Then the string was passed through the pulley and both masses were attached securely. With mass 1 position higher, we started recording and released the system, allowing the masses to move freely while the sensor collected the data. We then used the data to calculate the experimental acceleration, comparing it to the theoretical acceleration determined by the formula. In this case, we used A equals M1 minus B minus M2 over M1 plus M2 times G. Next, we introduced a second pulley to see how adding another loop affects the acceleration that we already had, and we again selected the masses, both heavier than 50 grams but less than 200 grams, so we could ensure the difference was more than 50 grams. After we assembled the two-pulley system, we repeated the procedure, collecting the data until we obtained a clean, linear graph of motion. Finally, we tested the different combinations of masses to find that one produced an acceleration as close to zero as possible. We compared the percentage errors between both setups, and then we discussed possible sources of error, such as friction in the pulley, uneven surfaces, or measurement inaccuracies.
So table 1, for mass 1 we did 10, mass 2 80, and then after plugging in those numbers for our acceleration, our theoretical was 7.62. For table 2, after we run the experiment, we had a acceleration of 4.74 and a percent error of 70%. And for table 3, we used two pulleys. So for mass 1 it was 130, mass 2 40. Our theoretical was 3.37. For table 4, after we ran the experiment, we had an experimental acceleration of 7.27 and a percent error of 53. The percent error today was greater. The reason why we believe this is because we probably got confused with the masses, and we used the wrong points of the graph. Between the two setups, the one that had a more significant error was the first table. We believe what could have contributed to our percent error was using the wrong points in the graph.
Number 7, pulleys conclusion. In this lab, we investigated the motion of an Atwood's machine to study how mass differences affected acceleration in both a single pulley and a double pulley system. The results supported Newton's second law, showing that as the difference between the two masses increased, the acceleration also increased. The experimental acceleration values were close to the theoretical predictions calculated for the single pulley setup and the modified expression for the double pulley system. However, small discrepancies were observed due to the friction in the pulleys, slight imbalances, and air resistance, which caused the experimental accelerations to be slightly lower than the theoretical values. The percent error for the single pulley setup was smaller because the system was simpler and had fewer frictional losses. The double pulley setup, on the other hand, showed a high percent error since it introduced more friction, additional pulley mass, and smaller accelerations that increased the relative uncertainty in measurement. Other factors that may have influenced the results included the limited height of the setup, potential system calibration errors, and variation in how smoothly the masses were released. Overall, the experiment effectively demonstrated the relationship between net force, mass, and acceleration. The data trends confirmed the theoretical expectations, and the observed errors provided valuable insight into real-world mechanical limitations. With improved pulley alignment, reduced friction, and more precise sensors, the accuracy of the experimental results could be further enhanced.